Okay, let's try to continue our class of design of embedded wall. I think last time we did basic of design. Okay, this time we are going for the limit equilibrium method. This part is mainly for ultimate design. Okay, how to estimate the ultimate capacity of embedded wall. So it is the fourth video of this chapter, this class, this course. Okay, so let's go then. The basis, not the basis of design, but limiting equilibrium method. Okay, so limiting equilibrium method. This method or these methods are commonly used to estimate, to evaluate the penetration of a retaining wall required for, and also the internal forces and load in pops, like in this case, or anchors. So this means we use equilibrium method to estimate several things, starting from the embedment, okay? How deep the sheet pile has to go in the ground. For example, here you have D here or D here. But not only that, we also use it to estimate internal forces, load in the pop. For example, this here, we can see the support. What is the maximum load in this support? So we use this equilibrium. Okay, so this method assumes that the ground full strength is mobilized uniformly around the wall. Okay, which is not 100% true. For cantilever and top popped wall, for example, this one, on the top you have this support. We determine it statically determined and can be analyzed using limit equilibrium method, this kind of wall. Okay, so if you have then multi-popped wall, for example, you have several support, these walls are statistically indeterminate and require major simplification for such to do this kind of analysis. This means if you have only, for example, this one at the top, this support, it's possible to use limiting equilibrium to analyze this. But if you have several support at several position, then you need a lot of simplification to be able to analyze it. Otherwise, it's not possible, not advised to use static limits equilibrium. Okay, so let's talk about several conditions. First, fixed F condition. What does it mean exactly? You can see this. It means under this condition, the embedded wall is assumed to rotate around this point, which is not the tip of the wall of the pipe. It will rotate around this, okay? So that you will have the active and passive pressure on both sides, okay? And this rely on the surrounding ground for horizontal and moment equilibrium. So above this point, you have point here. Above this point, the retained side. This is the retained side. Yeah. So you can see easily that you have active earth pressure at this point above it at the retained side. Okay, but above this point at this side, excavated side, it is passive earth pressure here. Then if you take below, it will be opposite. For example, below this point, this is passive, this is active. Okay, this method is fixed earth condition. Okay, earth pressure reduced from at rest means K naught to active Ka, active earth pressure coefficient. Okay, the earth pressure coefficient from K naught to Ka, active earth pressure coefficient on the retained side. It means this side, because when the earth is active, it means it's getting loose. So the the coefficient, which is just the ratio between the horizontal stress to vertical stress. I think everyone knows that K naught when it is static, then when the soil start moving to push on the wall, which is active, then the horizontal stress, of course, will decrease. That's why the the Ka is less than K naught. Okay, but if you go to this side to passive, because passive means the wall is pushing on the soil, and you can guess easily what will happen when this wall pushes on this ground. Okay, it will make the soil like denser, compact. That's why the passive earth pressure coefficient Kp is higher than K naught or Ka. Okay, so it means we have Ka less than K naught, which is also less than Kp. Okay, so below this point, I think it's easy to guess. We have the retained side become passive. Okay, here below this point, this is passive, but this side, excavated side, is active. It's simply like that. Okay, so it means the earth pressure rise to our passive on the retained side, okay, and fall to active on the excavated side, passive to active. Okay, passive means the wall is pushing on the soil. Active means the ground is pushing on the wall. Okay, so in practice, the earth pressure below, okay, below this point are often replaced by equivalent reaction. Okay, just replace it by reaction. You can see here simplified to reaction like this, instead of using this kind of mm, active and passive earth pressure. So to do that, to compensate the required embedment depth, DO, D0, if you mean, for example, this one, you can see that this is from the surface, bottom of the excavation to this point of rotation. Okay, so if you want to simplify it, you just go to this one, D, where D is like this one, 20 plus 20%. It means 1 point times D0. Okay, so to compensate, you replace this, but the embedment D